Welcome to Ready to Derive. In this video, we use the limit definition of a derivative to derive the derivative of sin x. Sorry, that's a mouthful. But in the interest of time, we find the derivative of the other three functions using a more graphical, intuitive approach. All these derivatives are going to be super useful moving forward in calculus. So we end with a couple of practice problems. This is a short preamble because not much to say here, except be prepared to have your mind blown when the derivative of e to the x is revealed. So let's start with sin x. And we're going to begin with a graphical approach to finding the derivative. And then we will move on to proving it using the limit definition. So when graphing derivatives of functions, it's always good to look for points where there are horizontal tangent lines, because wherever there's a horizontal tangent line, as I've indicated at these points here, we know that the slope at that point is 0. So I can translate, so the bottom graph is going to be the beginning of the derivative graph. So I know that where the slope is 0 at those, the max and mins, here at negative pi over 2 and at negative 3 pi over 2. And then the next thing to do is to look for where the slope is 1 or negative 1. So it looks here, now that might look more like a slope of a half, but you have to trust me on this that it's actually a slope of 1. It's just the x and y axes on sort of evenly calibrated. So the slope there at x equals 0 is 1, so I'm going to record that on my derivative graph. And by symmetry, therefore, the slope at pi must be negative 1, and at 2 pi must be positive 1 again. So if we just follow that pattern along, we get this these dots, and then if you connect the dots, so you should see a familiar function being formed, and this indeed is cosine x. So the derivative of sine x is cosine x. And another little feature to kind of keep an eye out for in terms of helping you make these graphs is if you just look at where sine x is increasing. So sine x is increasing, or this is any function. You could do this for any function. Wherever that function is increasing, we know that the derivative should be positive because it's increasing, the slope is positive. Therefore, the corresponding derivative graph in those regions the portions of the graph should be above the x-axis. So anywhere where the original function is increasing, so let me just write this down. So if wherever f is increasing, that's going to imply that f prime has to be positive or above the x-axis. And similarly, where f is decreasing, you're going to look to make sure that f prime, the graph of f prime, dips below the x-axis and is negative. So let's do a proof of that the derivative of sine x is cosine x. So if you ever want to prove a derivative, you have to invoke the derivative formula, the limit definition of a derivative. In this case, f of x is sine x. So if we replace f of x plus h and f of x in the numerator, we end up with this. Now, be careful here. It might be very tempting, as I've seen students do this before, so do not take notes on this because I'm going to show you something that's illegal, is to think that you could just break this up as sine x plus sine h. But you have to think to yourself, what property are you using? And if you think distributive property, well, then you got to think again, because sine is not a number that's multiplying into x plus h. It's a function. It's an operator. And so you cannot just break it apart like that. You have to recall a property of sine, the sine of the sum of the two angles from pre-calculus. So this is in fact how you would break it apart if you want to release things from the parentheses. So sine of a plus b is equal to sine a cosine b plus cosine a sine b. So let's replace that then here with, but instead of a and b, I'm using x and h. So this would be sine of x cosine of h plus cosine of x sine of h minus sine of x. Just extend that a little bit. And now, what do we do? Where do we go from here? So this is, I'm looking for two terms that have a common factor. It looks like sine x cosine h. These are the only two terms that have a common factor. So I'm going to rewrite I'm just going to restructure a little bit, and I'm going to write sine x. I'm actually going to factor out of cosine h, and then I'm going to put a -1 to make sure that when I distribute back in, I get this minus sine x. And then I have plus cosine x sine h still remaining. Now, I can also break this apart and just say that it's h is going into, h can kind of be divided up and can go into this term here and also this term. So h is dividing equally into both of them. That's really the same as distributing. And so by the limit laws, because I have the limit of a sum of two function, I can actually separate it as the sum of the limits of the individual functions. And you will notice that I have sine x and cosine x are in blue, and that is for a reason. And the reason is that this sine x here and cosine x here, they do not have h in them. So the fact that I want the limit as h goes to 0 doesn't really matter. They play no influence in this limit. So I actually can treat them like a constant and bring them to the front of the limit statements. So let me just bring up the expression for the derivative from the previous slide. And just to reiterate, both sine x and cosine x, because they don't have h's in them, they're independent of h approaching 0. You can treat them like constants and bring them in front of the limit. So this expression becomes this. And now these two limits here, these are limits that we're not going to prove right now because it would take a long time to do so, but they can be proved using the squeeze theorem from the first unit on limits. Instead, we're going to take a graphical look at them. So in this graph from Desmos, I graphed cosine h minus 1 over h, and you will notice that the limit as x approaches, as h approaches 0, of course, when I typed it into Desmos, I typed cosine x minus 1 over x. It doesn't really matter. As h goes to 0, this approaches, this limit is 0. And for sine x over x, or sine h over h, as h approaches 0, it looks like it's approaching 1. So I'm going to replace these limits with what they're actually equal to. And then you will notice that because sine x times 0, this disappears. And we're just left with cosine x, which proves that if f of x equals sine x, then f prime x, its derivative, is cosine x. Let's move on to a graphical approach to the derivative of cosine x. Once again, we look for places where the tangent line is horizontal. So at 0, at pi, at 2 pi, negative pi, negative 2 pi. And because the slope there is 0, that provides us with our x-intercepts of the derivative graph. And then if we take, let's go and see where the slopes are 1 and negative 1. So here at negative pi over 2, it seems to be about 1. At pi over 2, it's symmetrical but negative, so negative 1. And you can kind of fill in the gaps, the pattern, and then as you connect it, a somewhat familiar function appears. You might wish it was sine x, just because it would be really nice if the derivative of sine x is cosine x and vice versa. But it turns out that the derivative of cosine x is negative sine x. So we'll just leave this at a graphical approach. You could prove this in the same way we proved that the derivative of sine x is cosine x, but that's quite lengthy and it really goes through the same motions. So let's look at the graph of e to the x and figure out what the derivative of e to the x is by actually trying to sketch its derivative first. So do notice that on the e to the x graph, there's no place where f prime is equal to 0, right? There's no kind of turning points or max or mins. In fact, it seems that e to the x, if we say f equals e to the x, it's always increasing. And if that is true, that means that its derivative graph always has to be above the x-axis or positive. So nowhere where f prime equals 0, so I'll go for the next best thing, which is, it looks like at x equals 0, looks like the derivative there is 1. I'm pretty confident about that. And then maybe at x equals -1, we have a fraction. Maybe it's about a third. At x equals -2, it's even shallower. And you can imagine as you continue along further out along the curve, the slope is getting closer and closer to 0. So we have something like that. We definitely have an x, we have a horizontal asymptote along the x-axis. Now, up here at x equals 1, I'm going to go to, now this slope here looks like it could be somewhere between 2 and 3. So I'm going to sketch that right there between 2 and 3. And obviously the slope just keeps getting steeper and steeper. So I can kind of finish off, I can kind of conjecture, it's not very accurate, that the graph is going something like that. Well, it turns out that the slope here is not just somewhere between 2 and 3. It's actually around 2.7 something something. It's actually exactly e. So the slope at x equals 1, this value here, is the number e, the irrational number e. And it turns out that that is also the value of the function at x equals 1. So, not surprisingly, the derivative of e to the x with respect to x is indeed e to the x. It's itself. It's the only function whose derivative is itself. If it were 2 to the x or 10 to the x, the shape would look familiar, but it wouldn't, it would resemble the parent function, but there would be a slight adjustment. So the derivative of 2 to the x is close to 2 to the x, but not quite. But e to the x is that special function whose derivative is itself. So let's actually do a proof, or more like a quasi-proof, of the fact that the derivative of e to the x is e to the x. Quasi in the sense that, once again, you have to accept that a certain limit statement is what I tell you it is. We're not going to prove that because it would make this too long. So let's recall the definition of the derivative again. And our function is e to the x. So we are going to substitute e to the x into there. That's why we get e to the x plus h minus e to the x over h. The limit of that is h goes to 0. And we have to do something algebraically to this. So the best bet is to say, well, by the rules of exponents, I could rewrite that e to the x plus h as e to the x times e to the h. And of course, I have this minus e to the x. Not much else I can do there except maybe factor out e to the x. So e to the x is factored out, left with e to the h minus 1. Once again, as in the case for sine, because this term does not have an h in it, it is independent of the limit and we can bring it in front, treat it like a coefficient. So we get this, left with this. And that orange function is graphed just below. So we can see that as h goes to 0, the limit appears to be 1. And that's the fact that you're just going to have to accept. It is indeed 1, that quantity. And so we replace it with 1, and thus quasi-proving that the derivative of e to the x equals e to the x. But this expression, this limit is very, very important because the fact that it is equal to 1, e is the only number that makes it equal to 1. So actually the definition of e is that it is the number that makes the limit of this expression equal to 1. So if I replace that with like 2 to the h or 10 to the h, the limit would not turn out to be 1. It would be slightly different. So this is what's special about the number e and why it's such an important base in mathematics, because the derivative of e to the x is e to the x. So now we'll take a look at the derivative of ln x. ln implies that the base is e. Later in the course, we will look at other bases for log and other bases for exponential expressions, but these two derivatives are the most straightforward of all the logarithms and exponents. So let's draw this there, and we see once again that again f equals l log of x, ln of x, sorry, is increasing again. So therefore, its derivative graph is going to be positive, or all slopes are going to be positive. The derivative graph is going to be above the x-axis. but in a slightly different way than when we were dealing with e to the x. So I go, again, no places where the derivative is equal to 0. So I'm going to go straight for where the derivative appears to be 1, which is at x equals 1. So I'm going to plot that derivative here. And then I'm noticing now that if I go to, let's go to x equals 2. X equals 2, the derivative looks like it's a half. X equals 3, even more shallow. And so we see that as x goes to infinity, the derivative is getting closer and closer to 0. So once again, we have a horizontal asymptote along the x-axis. Now what's happening on the other side, well, of x equals 1? It looks, obviously it's getting steeper and steeper. It's a little hard to gauge how steep that is. In fact, it's heading towards, it seems like if we continue along, the slope is getting more closer and closer to positive infinity. So if we make that inference, what we do is we create this graph, and this graph might not sort of pop out immediately. You might think it's an exponential graph in reverse, but actually that graph is half of the graph of 1 over x. Only for x is greater than 0, because you cannot take the logarithm of a number unless it's bigger than 0 to begin with. So yeah, so this is the graph of 1 over x, and the slope, just to confirm, the slope here really is 1, and at x equals 2, the slope really is a half, because it's just 1 over 2, and x equals 3, the slope is 1/3. X equals 4, 1/4. So, and if you went to x equals a half, the reciprocal of that would be 2. So it's a pretty neat derivative. Very, very simple and straightforward. So we'll end with a couple of practice examples. So let's look at this function, x plus 2 cosine x. And our first step is going to be find the equation of the tangent line to f at x equals 0. Well, let's call up the equation of a tangent line. Remember, it's y minus y1, but we can just say y1 is f of a, and x minus a, that's x1. And the slope, of course, is going to just be the derivative of the function at that particular value. So let's kind of organize this. Whenever I'm doing equation of tangent lines, I kind of like to have things set out in a nice, neat manner. So the first thing I do is get that derivative function. So the derivative of x is 1, and the derivative of 2 cosine x, well, the derivative of cosine is negative sign, and we just have that coefficient in front. So we have that. And then we can, we're interested in at 0, so now I need to find f of 0. So plugging 0 in here, 2 cosine 0. Cosine 0 is 1, 1 times 2 is 2. That value is 2. I also get to plug 0 into the derivative formula, and I get 1 minus 2 sine 0. Sine of 0 is 0. That leaves me with 1. And then I just plug in. So f of 0 is 2, so y minus 2 equals, the slope is 1, and then x minus 0. If I put that into slope-intercept form, which you're not required to do, but that would be y equals x plus 2. And let's have a look at a graph of that function. And it does indeed look like, if we go to x when x is 0 here, does indeed look like the y-intercept is 2 and the slope is 1. So that seems to corroborate. And now we're going to find all the values between 0 and 2 pi where the tangent line to f is horizontal. So what are we looking at here? Maybe use a different color. So it looks like it's horizontal there, wherever that place is, and also here, wherever that is. It's also horizontal here, but that's beyond 2 pi, so we don't really have to consider that. So how do we find out where the tangent line is horizontal? Well, we know that's when the derivative is equal to 0. So we just have to take the derivative expression, which we got above in part A, set that equal to 0. And if we rearrange 2 sine x will equal 1. So you could just demonstrate to yourself that that's true. And that means that sine of x equals a half. Well, there's a lot of places where the sine of x equals a half, but we only need to find it from 0 to 2 pi. So what I like to do first is to sort of acknowledge the reference angle. The reference angle, the angle whose sine is a half, its base angle is always going to be something like pi over 6. And because sine is positive, we know that we have to be in, that angle has to be placed in quadrants 1 or 2. So, well, quadrant 1 is pretty easy. It's just pi over 6 is what it is. But to place in quadrant 2 a reference angle of pi over 6, it means that this angle has to be pi over 6, and that leaves the angle itself. The angle of rotation that you would take you from here to here is 5 pi over 6. So the answer to this question, there's two answers, pi over 6 and 5 pi over 6. And that is that's kind of hard to mark on the diagram, but that's the location of those 2 points where the tangent line is horizontal. And we'll end with this last practice problem. Consider this curve, y equals e to the x minus ln x. We're going to find the equation of the tangent line to the curve at x equals 1. And it's a little diagram just to provide us a reference. So I've changed the notation. I'm not using f of x, but you could always replace y with f of x if it's easier. So again, I'm going to kind of set it up. So e to the x minus ln x dy by dx, using appropriate notation, is, well, the derivative of e to the x is itself, and the derivative of ln x is 1 over x. Now, here, when we plug in, we're going to have to plug in x equals 1. There's no convenient way of writing this when you're not using function notation. So I'll say x equals 1, y equals e to the 1 minus ln 1. And e to the 1 is e, and ln of 1 is 0. So we have that y coordinate. So we basically, so at x equals 1, we know that the y coordinate is e. And now we need to plug x equals 1 into the derivative formula. So we get e to the 1 minus 1 over 1, which is just e minus 1. And so we can write the equation of the tangent line, y minus y1, which is e, equals the slope. Okay, it's a little complicated. So the e is about 2.7. 2.7 minus 1 means the slope is about 1.7, 1.72. And then we have x minus 1. And that is the equation of the tangent line. So here, we won't bother to simplify that because it's a little complicated, but that's the equation of this line. And just to summarize, in case you didn't get these formulas down, the derivative of sine x is cosine x. Derivative of cosine x is negative sine. The derivative of e to the x is perfect. It's just e to the x. And the derivative of ln x is 1 over x, but x has to be bigger than 0. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.